Okay, so let's do some more examples of determining intermolecular forces for particular molecules. So we did N2 and NH3 in the previous video using this flowchart to kind of guide us as to determining which intermolecular force is present. Let's go ahead and do CH3F. So we need to determine first, is that molecule polar? And the way that we determine if it's polar, you got to do the Lewis dot structure. So get your periodic table, get your electronegativity table in front of you again, so you can draw that Lewis dot structure, and hopefully some of those skills are still in your brain, and you'll see that to determine the Lewis dot structure for CH3F, you will have a total of 14 valence electrons. And when drawing that Lewis dot structure, the carbon is going to be the center atom. I'm going to scatter my outer atoms around it, the 3 hydrogens and the 1 fluorine. Then I'm going to make my single bonds, counting by 2. So 2, 4, 6, 8. I've used 8 of my 14 valence electrons. Complete the octet on the outer atoms. Hydrogen is happy already. It already has a duet. So I'm going to do my fluorines. I've used 8 already. 9, 10, 11, 12, 13, 14. I've used 14, all 4 of my available 14 valence electrons. So I have my Lewis dot structure. I see that my central atom is not attached to all the same atom. It's attached to 3 hydrogens and a fluorine. So that's going to make this molecule polar. And specifically polar, fluorine is more electronegative than carbon. If you look at your electronegativity table, you see that fluorine has the highest electronegativity value on that table. So if you wanted to draw the dipole, you would draw it with that arrow pointing towards the fluorine. But that molecule is indeed polar because not all of my atoms attached to the central atom are the same. So it is indeed polar. Is hydrogen bonded directly to nitrogen, oxygen, or fluorine? No, my hydrogen is bonded to my carbon. So I have a polar molecule, but my hydrogen is not directly bound to nitrogen, oxygen, or fluorine. So my intermolecular force that is present is going to be dipole-dipole and dispersion forces. Remember, all molecules have dispersion forces. So that would be for CH3F. We talked about carbon dioxide already in a previous video, but we can just talk through it again using this scheme. We want to identify the intermolecular forces in CO2. Is this molecule polar? Here's the Lewis dot structure. My X atom is all the same, so this is not a polar molecule. Is it ionic? Nope, it's molecular because all of my atoms are nonmetals. So the only forces that are present in CO2 would be dispersion forces. Let's talk about water. Actually, we'll talk about water with regards to NaCl aqueous in a second, but let's talk about NaCl. NaCl, solid. Hopefully you look at this and you see, oh, I see a metal and a nonmetal. That's ionic. So this is an ionic molecule. So what intermolecular force is present for NaCl solid would just be ionic forces. If I have NaCl that is aqueous, remember aqueous means in the presence of water, so that means a solution of NaCl. Since I have a mixture of something that is polar, water, and something that is ionic, NaCl, my intermolecular forces present there would be ion dipole.